Hello everyone. Today inshallah we will continue with vector spaces. Our main topic today is about the linear dependence and the linear independence. As you know from the previous lecture, but before going to this, I want to confirm that our second midterm, which is gonna come up, I believe, within December, I think, the second midterm. We spoke about this yesterday, say that, I think.
Yeah.
It will be in December, yes?
We have the exact date.
Yeah, please try to see it. It will cover the rest of our course, yes? 11th. It's gonna be Thursday, am I right?
Yeah.
Yes, I think,
Yeah.
I guess so. So, our next midterm will cover the parts from vector spaces till the end of our course. Okay, when we come to the slide, I will show it to you. So I need you to focus and start working with this because time flies. Today, I think we are by the end of October, and just only we'll start within the our next lectures will be within next week in November. So the time is really ticking. Okay. I want your attention. As I told you, we will continue on the topic of vector spaces. This is the slide that I want to speak with you with. So the coming exam will cover the 4 chapters, vector spaces, the rest of vector spaces, because the first part already we have it, but it will be included, of course. So vector spaces, linear maps, this is really important, the eigenvalue and eigenvectors, then the inner product and the part of the analytic geometry. Don't be afraid from the analytic geometry. It's really very simple. It's direct application on what we have studied previously, so it's going to be really very quick and easy, okay? But the main thing is I want you to start studying hard and solving problems after me as much as you can, okay? Let's start step by step. So I want to review with you starting from the part of linear combination. We already taught this yesterday. A linear combination is really very simple, which expresses that any vector belongs to a vector space can be generated from another set just by identifying the values of alpha 1, alpha 2, alpha 3, and they are scalars. Okay, these set of scalars, we call them coefficients, and the sequence and the arrangement is important, which means you will identify the values of alpha 1, alpha 2, alpha 3, and their arrangement, alpha 1 times u1, alpha 2 times u2, is important also, okay? So that's the meaning of a linear combination. In this slide, he's telling you about that any E of a vector space with the elements u1 up to u are elements of E, the set of linear combinations of vectors can generate this sub-vector space, and we will call them generators, and we can symbolize it by putting these vectors u1, u2 up to ur within this shape, and this shape stand for exactly like multiplying alpha 1, alpha 2, alpha 3 in those set of vectors, and we talked about this yesterday. Those are the generators. Also, the generators for a certain vector space is not unique. So I can generate a specific vector space or sub-vector space by various bunch of vectors, okay? We will come to the optimal one, which is the canonical. Like for R1, R2, R3, you know the canonical generators, which are 1 and 0, 0 and 1 for R2, or 1 double 0, 0, 1, 0, 0, 0, 1 for R3, and so on. We spoke about this, and we will come also to this topic. I believe this question is tempting. It's one of the questions that came previously in one of the exams. Whenever I get the chance to go through some of the exam questions, I will go with it with you. In this question, he is asking you, considering each of the indicated vector spaces, the usual operations of addition and scalar multiplication under these conditions indicate which statements are true. For the first statement, he is giving you Miss Nada, A, B, C, D, which is a vector, belongs to R4, such that both A and B is equal to 0, and B plus C plus D is equal to 1. Isn't a subspace of R4. Is this correct or not?
Yes.
We need to.
Huh? Yes, it is correct.
It's not correct.
It's not correct. So the statement, should I choose it or not choose
It's
it?
correct. It's correct. Statement صح.
How would you
يعني,
know?
yeah. So
عشان
which
في one.
means A is considered
عشان في one.
a sub is not is correct, which means this set is not a subvector space of R4. Are you sure?
Yes.
How did you came to this result?
عشان في one.
Yes, exactly right. More than perfect. Because as you remark, here's for A is equal to B, I can replace A by negative B. I can also from B, C plus D is equal to 1 once you get D or C equal to 1 minus B and D, and you just make your insertion. You will be able, for example, for the simplest try, if you want to search for the origin, putting A, B, C, D equal to zeros, you are not going to have this origin of R4. So yes, your choice is correct. Okay, for number B. Number B, he's asking you if A belongs to the set of n by n matrices, which is a squared set of matrices, such that each A is equal to 2 over A transpose. Is this a subspace of an n by n matrices? Yes or no? Why yes?
Transpose. Refresh.
قشطة.
For the origin, if you multiply by 2, it's still going to be an origin.
Okay.
So.
Do you have matrices which mainly do the relation or approve the relation of A is equal to 2A transpose? Can you think about the relation first? Mr. Ziad, the relation A is equal to A2 transpose.
It's an identity.
I think, no, it's not gonna equal. The identity matrix, the matrix equal the transpose. Am I right? But it's not equal to the twice of the transpose, okay? So what? I believe it's the origin. Yes, it's the zero matrix.
Yeah.
And once it is the zero matrix, it's considered a subvector space. So, yes, the first A is correct, and the second is correct. So for A and B are correct. Yeah. For C, yes, I'm sorry. For C, which is the set of A and the A square, of A and the A square, such that A belongs to R. Is it a subspace of R2?
No way.
Why?
بص بقى دي خدعة.
اه
يعني افتكر ان هي سب سبيس بس لا.
ليه؟ ماشي قول
عشان
لي.
في حاجة هتنخرف كده. في
أيوة،
القوانين
هي
بتاعت
إيه؟ ايوه
الابلكيشن.
الاديشن. الاديشن. If I have two vectors, A and A square, and B and B square, adding them together, you will have A plus B for the first component. The second component is going to be A squared plus B squared, which is not A plus B to the power of 2. You read what I'm saying? So it's going to be a failure. So this is okay. This is a correct statement. That's a correct statement. This is not a correct statement. For the origin, it will be okay.
Yes.
Okay? But for the addition closure, it's not going to be okay. Okay? Because you understand it, okay? Do you want me to write it down for you?
You can write it down, but
Okay. It's very, very simple. First, step number 1, in order to check a subvector space, I should check, I should check the origin. So checking the origin. If A is equal to 0, this is gonna lead to 0 and 0 to the power of 2, which is 0 and 0 is the origin of R2. So first is okay. The second part, if I have two vectors, V1, let's say A and the A square, and V2, which is B and the B square, if you try to get V1 plus V2, the result will be A plus B, and that's A squared plus B squared, which doesn't equal to A plus B, and A plus B to the power of 2. That's the definition of the addition closure. If you add two vectors together, the result should belong to the same set. This is not belonging to the same set. To be belong to the same set, A plus B must equal to A plus B to the power of 2. Am I right? So that's a failure in the closure. So it is not closed in addition. So it is not a sub vector space. Okay, it's very, very simple. Okay, for number D, any vector space E has a sub vector spaces E and the empty set. Am I right? Is it right? No. Why it's not right? It's partially right.
Yeah, the E is
The
right, the most.
More than perfect. Just if he just inserted here an origin, so it will be correct. Okay. For number E, let F be a subspace of a vector space E. I will read it once more. F is a subvector space from E. Okay. And then its U and V belongs to E. Okay, continue. If U plus V belongs to F, so the addition of them belongs to F, and U belongs to F, and U belongs to F, then V belongs to F. Is this correct? Yes. Yes, it is correct. Like, how to prove it is correct? It's really very simple. Okay, once more. Remark that F is a part of E, is a subvector space of E. Are we right? So F by itself is a vector space. Okay? So it's supposed to be closed under the addition and the closure under the scalar multiplication of vectors. Now you have U, which belongs to F. And the sum of both U and V belongs to F. Meaning U belongs to F, it means the negative U belongs to F. Are we right? So if we simply added negative U to the vector U plus V together, the result will be V belongs to F. Am I right?
Yes.
You have U belongs to the F, okay? And you have the sum of them belongs to the F. Once you have U belongs to F, so its inverse, which is negative U, is a part from F. So if you have negative U and the vector which is U plus V, it's one vector, okay? If you add them together, the result will be, and it's already belongs to F, so it's correct. So the correct statements, the first is correct, the second is correct, and the E is correct. The incorrect statements are C and D. What's really, I usually worry much about telling you or giving you the result with negation, not equal to or un. So you should read these statements more than one. Okay, more than once. Any questions?
معلش هو الامتحان من 20 صح؟
اه
10 أسئلة.
اتس نوت كل الاسئله اللي موجوده هو بيرتبها لان هو مش كل سؤال عليه درجه. يعني في اسئله في عليه 1.2 1.8 and so on. فاهمني بس؟ any questions؟ بعدين برضو لاحظ نقطه ثانيه. مفيش يعني صعب قوي ان حد بيقفل ال 10 questions كلهم لو هو جات التايم studying all of them all together. You read me? And somehow he will have to, if there is a statement he's sure about and he studied well, he will be able to.
طبعا عندي سؤال بقى.
اتفضل.
هو الناس في البرتغال نظام زينا كده؟
معلش ده ممكن نتناقش فيه بعد ما اخلص.
تمام ماشي.
Okay. Of course, I will test the 8 statements beside each one of these questions. Now I need you to focus with me because this part is new. He's telling you, we say that a vector space E is finitely generated, which means it will be generated from a finite set of vectors, okay? If there are R belongs to N, so it's a number of vectors, identified, determined, and you want till U R belongs to E, such that E consists of this set of vectors. So, for vector space E, the meaning of finitely generated, it means that you will have 2, 3 vectors that can generate this vector space. That's the meaning, okay? Okay, the following vector spaces are finitely generated. Of course, Kn, which means R1, R2, but we usually use K to stand for the real part or the complex part, okay? For a set of n by n matrices, the polynomials of certain degree, as we spoke previously about this, and all the vectors. For K over S, the set of polynomials in one variable x with coefficients in K is not finitely generated if K of S was finitely generated. That's, there exists R belongs to N, and there exists B1 blah 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 BR belongs to K of X. The expression or the explanation of this statement is in this subparagraph, which states that let K be the biggest degree. If you remember the polynomials, if I have K, which is bigger than the available degrees that you are dealing with in the generators of this set of polynomials, you are not going to be able to generate it. For example, if I have a set of generators of x to the power of 2, okay? If I want to generate x cubed, I'm not going to be able to generate it from x squared, because all the generations or all the generating of these vectors are based on adding, not multiplying these vectors in each other, okay? So, and this is by logic. So let K be the biggest degree between all polynomials, V1 and VR. Any polynomial with degree strictly bigger than K, other than K, you are going to be able to generate it from this set of generators. And it makes sense either in polynomials or in real or in Rn. Also, there is a very important in specific definition. Here let E be a vector space and U1 up to UR and V1 up to Vs be vectors of E. The following statements hold. Are you doing for it? From U1 to UR is a subset from V1 up to Vs. So, once more, let's read it once more. Let E be a vector space. So E is already a vector space. And let the bunch of vectors from U1 to UR and another bunch of vectors from V1 to VR be vectors of E. Both of them belongs to E. So either U or V belongs to E. The following statements is correct. Okay, U1 up to UR is a subset from V1 to Vs. When it's gonna be a subset? When each vector of these vectors can be a linear combination from those vectors. Mainly, I can generate each vector from these vectors from those bunch. You know how to generate vector from another vectors. Are you with me? Say that. Huh?
Yes.
Let's repeat it once more. If I have E as a vector space, and within E as a vector space, we have vectors. A bunch of them, subset of them, which is U1 to UR, a group of vectors. And I will have from this vector space another set of vectors. It contains plenty of vectors. I've just gathered some of them and the others. The other set is V1 up to VR. We can say that U1, U2, U3 is a subset from V1, V2, V3. When? What's the condition? If each one of these vectors is a linear combination from those vectors. What's the linear combination, ya Farid? The linear combination means that U1 is equal to alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3 blah 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 plus alpha R in times VR. So the first vector is a linear combination. You read what I'm saying? That's the meaning. And the V2, U2, the second vector, the second vector is also a linear combination from these vectors. Are you with me? For alpha 1, alpha 2, alpha 3, maybe they equal to each other, maybe some of them is equal to 0. Do you know what I'm saying? Because alpha 1, it belongs to the real number, the set of real numbers, or k in general. Same way like alpha 2 and alpha 3, they belongs to k. Huh? Does it make sense?
Yeah.
Okay?
Can it be the opposite way around?
Just a sec. This is the condition to have U as a subset of V. This is what's certain. If and only if this symbol or this subset gonna be satisfied, if and only if it happens that for all I, for every I in here, from 1 to R, from 1 to R of those U, Ui is a linear combination of the vectors from V1 and to Vs. So each one of them is a linear combination. Okay? There is none of the vectors in here is not a linear combination from these vectors. That's the condition of subset. Okay, when to say that they are equal to each other? So this set of vectors is exactly equal to that set of vectors. When it's gonna be? If each set of these sets can be generated from the others. This is what you said. So I can generate U from this set. Any vector in here, I can generate it from those vectors, and vice versa. And the vectors from V also can be generated from U. Also written here, if and only if for all I, for every vector in here, can be generated as a linear combination from this set, and vice versa for every vector in V can be generated from U. This is when you say that this group of vectors is exactly equal to that group of vectors, and both of them belongs to a certain vector space. This slide, it's all about if I have certain, if I have certain set of vectors and they can generate a vector space, but between this set of vectors there is one vector which is a linear combination from the others. Okay, I can take this vector out and still able to generate this vector space. For example, if I have, let's say, the vector 1, 0, and 0, the vector 0, 1, and 0, and the vector 0, 0, and 1, and the vector 2, 0, and 0. For example, if you look to those 4 vectors, those bunch of vectors can generate R3. Am I right? 1, 0, 0, 0, 1, 0, 0, 0, 1. I can simply remove this vector and still be able to generate R3. Am I right? Because this vector is a linear combination from all of them or from any of them. Do you understand what I'm saying? So the statement here is simply, if you have from U1 up to UR, and those vectors of vector space E, and there is 1 to R such that UI is a linear combination of the remaining R minus 1. So one of these vectors is a linear combination from the others. I can take it out. Okay? I can drop it. So this, it's exactly like they were equal to each other. So this set is equal to that set exactly. This vector, it's not going to do a difference in the forming of this vector space. Okay, and also it's written here and expressed in the dates. This slide is really very important. So the previous slides show you that I can drop one of the vectors if it is a linear combination from the other vectors. In this, how I can minimize the set for generation. So I can get to the optimal set for generating a certain vector space. معايا مسندة? Okay, for this set, or for this slide, if I have S, which is vector 1, vector 2, vector up to R, يا فريد ويا زياد, be a sequence of elements of vector from E over A. And the S dash, which is U1 dash, U2 dash, U3 dash, UR dash, be a sequence obtained from S by applying transformation of the following type. What's the transformation? I'm going to play with the row operation. Do you remember the row operations? Which are switching rows, multiplying row by a number, multiplying row by a number and adding to another row. That's the bunch of operations. They will be the same, which is a huge statement. So once more, if I have a bunch of vectors, okay, a bunch of vectors, and if you want to use the row operations to change their shape, it is possible. And the new set will develop or generate the same vector space. That's a huge statement. So I can reduce the number of vectors and the shape of vectors. Am I right?
Yes.
Okay, very good. Then U1 up to UR generators, it's exactly like the equivalent vectors that will be generated by using the row operations. Okay, from the previous result, if we have m vectors in Kn arranged as lines, if I have them as rows in matrix A, and belongs to an m by n matrix, we can apply to a finite number of elementary transformations. This is how I will get an equivalent matrix with rows also, and the rows will be the sequence of vectors that I will use. You understand what I'm saying? Okay, so A, using the row operations, you will get A dash, and from here, then the subspace generated by the lines of A equal the subspace generated by the lines of A dash, which means if A is equivalent to A dash through the row operations, they can generate the same vector space. So this slide and the previous one introduced to you two important things. Number one, I can remove vectors till I reach the linearly independent vectors. What are the linearly independent vectors? The vectors that can't be generated from each other. They are completely different than each other. You repeat? That's the previous slide. This slide tells you also that I can change the shape of these vectors and reduces them to an optimal set that will help me to generate the same vector space, okay, or subvector space. Okay, here I want to talk with you with the linear dependence and the linear independence. I will have to read the slides in order to overcome the true statements, or if there is a statement that you need to find the true answer as the questions that you saw previously. But after I finish it, I will give you the summary of all of this. Okay, let E be a vector space, and U1 up to UR belongs to E, where R belongs to N. Remark, for R equal 1, if R is equal to 1, what's the meaning of R equal to 1? You have just only one vector. R is the number of vectors, R1, R2, R, 1, 2, 3, up to R. So if R is equal to 1, I'm talking about one vector. We say that the sequence U1 is going to be just only one vector. Or that's the vector U1 is linearly dependent when U1 is equal to K to 0. So if you have just only one vector in a set, and this vector is equal to 0, then it's a linearly dependent set. But if you have one vector that's not equal to the origin, it's linearly independent. I'm talking about the case of just only one vector. If you have more than one, vector, okay, for R greater than or equal to 2, which means if you have a set for more than one vector, it is a linearly dependent sequence. When is going to be a linearly dependent sequence? If one of these vectors can be generated from the others. Or that the vectors U1, UR are linearly dependent when at least one of the vectors of the sequence is a linear combination of the other vectors. So that's the definition of dependency or not dependent. So once more, what's the independent set of vectors? The set of vectors that can't be generated from each other. Okay? What's the dependent set of vectors? That's one or more vectors can be generated from the other vectors. If we are talking about one set, or a set, set with one vector, if this vector is the origin, so it's going to be linearly dependent. And that can be a statement to state if it's true or false. Okay? Answer. Prepare the question and give it to me. Okay? The second slide will be talk in specific about how to check a bunch of vectors if they are linearly independent or linearly dependent. All I have to do, as Mr. Farid said yesterday, is to solve this homogeneous system of equations. All I have to do, if I have a bunch of vectors, I want to know if they are linearly dependent or linearly independent. What to do? I will try to solve this system. K1, V1, K2, V2, K3, V3, blah, 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 blah. But it's gonna equal to not any vector. It's gonna equal to 0. I will solve for the values of K1 and K2. If it gives you a unique solution, if this system ended up with a unique solution, when the system ended like a reduced echelon form or a unique solution, that means the only solution for this to happen is to have K1 up to Kn equal to 0. So it's a linearly independent set. But if you try to solve this system يا فريد, and you ended up having a consistent but infinite number of solutions, it means one of these vectors is a linear combination from the others. So how to check a bunch of vectors to be linearly independent or to be linearly independent? I'm sorry, dependent يعني. Just put them in an augmented matrix. But this augmented matrix will solve a homogeneous system. If this, of course, a homogeneous system will be consistent forever. One of the questions that just hit my mind. Is it possible for a homogeneous system to be inconsistent?
No. دايما هيبقى فيه solution.
دايما هيبقى فيه solution. جدع يا راجل. The solution will be either two things. Either unique solution, والunique solution يحصل امتى؟ لو all elements equal to 0. طيب ال infinite number of solutions هيحصل ان في some variables will depend on the nature of the others. So if it is just only the unique solution that K1 up to Kn must equal to 0, then they are linearly independent set. If there is infinite number of solutions يا فريد, يبقى it is linearly dependent set. Okay? تعال try a question. Everything is stated here. We already passed through it. Here is mentioning that let E be a vector space over K, U1 up to UR be vectors of E, and the vectors U are linearly independent if and only F. Way to write 0E as a linear combination of these vectors. This is why I'm using this equation. If you try to solve it from alpha 1 up to alpha r, all of them is equal to 0, so it's going to be an independent set of vectors. If you have a relation connecting them, then it's going to be linearly dependent. I would choose this problem just to discover if this set of vectors linearly independent or linearly dependent. What to do if you are asked to just to go through it. All I have to do is to solve the system, which is simply gonna be on the augmented matrix on this form. The first vector will play the role of the first column. The second vector will be the second column. And the last vector will be the last column. And of course, for the results, it's a homogeneous system. So I'm solving AX is equal to 0. That's the system we're dealing with. So start solving this system using the main row operations that you already know. Okay, I will multiply the first row by negative and add it on the second row. Okay, so it's gonna come up to, if you multiply in 2 and add, it's gonna be negative 2 plus 2 is gonna be 0, negative 2 plus 1 is gonna be negative 1, negative 2 is gonna be negative 1 and 0. The first row is 1, 1, 1 and 0. The last row 0, 0, 1 and 0. Simply I can add the second row once more on the first row. So if you did this, I will have 1 double zeros and 0. Multiply the second row in a negative 1. So it's gonna be 0, 1, 1 and 0. The last row already 0, 0 and 1 and 0. So multiply by negative and add on the second row, it's gonna be 0, which means you have a unique solution. That's alpha 1 is equal to alpha 2 is equal to alpha 3, and they are all equal to 0. Of course, when I hit this result, I know that I will have a unique solution. طب ليه يا ندى؟ ليه ممكن اقف هنا وابقى ان انا عندي unique solution؟ لان الرانك بتاع السمولر ماتريكسز كام؟
3.
3. And you have how many variables? 3. Then you will have a unique solution. So I'm not searching for solutions. I'm searching to understand what's the nature of the solution. So if the rank is equal to the number of variables, to the number of the given vectors, so it's a square matrix with 3, so the rank will be 3, which means it will develop a unique solution, so all of them is equal to 0. So this set of vectors are linearly independent. Okay? Once more, just to do so, we will have to find K1, K2, K3, or alpha 1, alpha 2, alpha 3. Just once you do the substitution, the result will be equal to 0. I'm multiplying K1, K2, K3 in those vectors equal to 0, put them on a matrix form. That's the general form of the equations. It's going to be on this form. Just to try to manipulate in order to get the solution. It's a reduced echelon form. Developing that K1, K2, K3, all of them are zeros. So this set of vectors are linearly independent. It's very, very simple. Once they are linearly independent, it means this set can generate the vector space, which is a subset from R3. Are you with me? Okay, and we will call them down the road basis. And we will know that it's dimension 3 down the road. All of this are definitions will come. Okay? Okay, for other bunch of vectors, this is 1, 2, 0, double 1 and 0, 0, 1 and 0. Are they linearly independent? So I will do exactly the same. Searching for K1, K2, K3. So developing the system of equations. The system of equations starting from the beginning. It's, as you can see, it's 2 equations in how many variables?
3.
So bye-bye for the unique solution. Okay? So continue. Try to get a reduced echelon form. That's the reduced echelon form. Which means K1 plus K3 equal to 0. So the value of K1 will depend on the value of K3. Actually, K1 is equal to negative K3. Do you read me? And from the second row, K2 is equal to K3. Now I have infinite number of solutions. So I have a combination linking those vectors